Figure 12 shows the path of a projectile launched from what I'm assuming is meant to say level ground with a speed of 25 meters per second at an angle of 42 degrees to the horizontal. And then we're trying to work out the horizontal distance from the starting point of the projectile when it hits the ground. So we're trying to work out, in that case, this distance over here, which I'll call x. So this is a SUVAT question. Whenever you see projectiles, it's very often a SUVAT question. So the first thing that you want to do for these kinds of questions is draw out a SUVAT table and then figure out what the different quantities are, S, U, V, A, and T, in both the vertical direction and in the horizontal direction. But before we start entering in quantities, we want to define a positive direction. So all of these quantities, S, U, V, and A, are all vectors, and in the vertical direction, they can either be pointing upwards or pointing downwards. We could have a positive or a negative displacement, same with velocity, same with acceleration. So for our vertical components, we want to define a positive direction. That can be an arbitrary choice. It doesn't actually matter if you say upwards or downwards is positive. You just have to pick a direction and then stick with it. So I'm going to say that upwards is positive. So we have to now stick with this positive direction for the rest of the question. So if that's the case, the acceleration will be negative 9.81. Acceleration is downwards. And just quickly going back to sign conventions, we only need to define a positive direction for the vertical direction. Horizontally, it makes no difference because our projectile never goes backwards and forwards horizontally. It just continues to move forwards. So all of our quantities in the horizontal direction will always be positive. So, because the object starts and lands on level ground, that would mean that the vertical displacement is 0. So it starts here, it ends here. In the end, it's at the same height that it started at, so the vertical displacement will therefore be 0. Horizontal displacement is x, that's what we're trying to work out. Let's look at velocities now. So we have the velocity, 25 degrees at a particular angle. We need to work out the vertical and horizontal components of that velocity. So using SOHCAHTOA, with this being our hypotenuse, this being our opposite, this being our adjacent, we can say that this side will be 25 sine 42, and this side will be 25 cos 42. So these are the two velocity components horizontally and vertically. So we can now put these things into our table. So the initial vertical velocity would be 25 sine 42. Initial horizontal would be 25 cos 42. Now in the horizontal direction, because we ignore air resistance, there is only one force on our object, which is the downwards weight force. So horizontally, there is no resultant force. And if there is no resultant force, well, that will mean that there is no acceleration. So the horizontal acceleration is always 0. And if the horizontal acceleration is always 0, that means the initial speed is always equal to the final speed. But generally for SUVAT tables, to save time, I never bother by filling in these two quantities, the final speed and the acceleration. And the reason I don't bother is because the only equation that we use in the horizontal direction is speed is equal to distance over time. So speed is equal to distance over time. That's the only equation we use in the horizontal direction. All of the SUVAT equations assume that there is some acceleration. So if you were to actually put into your SUVAT equations, acceleration is equal to 0, you'll end up fundamentally with just two equations. You'll end up with initial speed is equal to final speed, which makes sense. If there is no acceleration, the velocity won't change. And you'll also end up with speed is equal to distance over time. So these are the two equations you'll end up with when you put acceleration to be 0 into your SUVAT equations. So, what else do we have? We don't know what the final velocity is in the vertical direction. The time I'm going to call t, we don't know what that is. If we want to work out what the horizontal displacement is, we need to work out the time in the horizontal direction. And the time in the horizontal direction is the same as the time in the vertical direction. These two times are always the same thing. So if we want to work out displacement horizontally, we then have to work out from the vertical direction, we have to work out what t is. We can then use speed is equal to distance over time for the horizontal direction. to work out what x is. So for the vertical direction, we have s and u, and we also have a and t. So the equation that relates all of those things will be s is equal to ut plus half at squared. S was 0, so 0 is equal to ut plus half at squared. I'm going to solve it algebraically first, just to save time. So then I can factorize out t, so t times u plus a half at is equal to 0. That gives me two solutions. T is equal to 0, and u plus a half at is 0. So it's not going to be t is equal to 0. That will obviously just be our start point, which is not the time that we're interested in. So we would be considering this equation. So rearranging that, we get a half at is equal to minus u, at is equal to minus 2u, t is then equal to minus 2u over a. Let's put in our quantities now. So u in the vertical direction was 25 sine 42, and a was minus 9.81. So minus 2 times 25 sine 42 all over minus 9.81, and we end up with our time being 3.410 seconds. So then we can use our horizontal direction. Let's just first put in that time into our table so we know what we have. We have 3.410, 3.410, and finally we can then do the speed, so 25 cos 42 in the horizontal direction, that is, multiplied by the time, 3.410, and we end up with 63.4 meters, which will then be d.